Okay. So I hope my screen is visible to everybody. Somebody please confirm.
Yes, sir.
All right. So we will see in the previous class we have seen the concept of isoparametric element, and no, sorry, we have seen the concept of this linear strain triangle. Okay, that is the triangular element with the natural coordinate system, that is in terms of xi and eta. Since time is not there, I am not going to cover a numerical on this. Okay, we have to cover an important topic today, that is the rectangular element. Okay, so let me create a rectangular element. Okay, so right. So in the previous class also we have seen the rectangular element, but in that class we have seen the rectangular element with the Cartesian coordinate system. Okay. So now we will see this rectangular element with the help of now the natural coordinate system. So now in the natural coordinate system, what we are assuming is this. So this is our rectangular element. Okay. And in this rectangular element, we are assuming the coordinate system like this, right? And here we will be having the xi value, that is the x direction, and this is the eta value, so this will be your y direction kind of thing, right? Now in this case also we are going to consider four nodes. Okay, in last class also, in the last previous lecture, we have considered this nodal connectivity. This is node number 1, this is node number 2, this is node number 3, and this will be your node number 4. Okay, now since this is in the natural coordinate system, it will be having the length and width as 2. The distance will be maximum 2. So here you will be having the origin. Okay, so this will be origin, which is having coordinates 0 and 0, and this will be the third coordinate. Okay, so this will be third node, it will be having 1 and 1. Okay, because in the x direction or the z direction and in eta direction, the maximum distance covered in the natural coordinate system is 1. Okay, so this will be also 1, but y value will be -1. This will be -1 and -1, and this will be x value or the xi value will be -1, but this eta value will be +1. Okay, so these are the nodal coordinates which we are assuming in the x and y, or rather I should say xi and eta direction, right? Now in this case we are going to assume the nodal deformations also. So in the xi direction, let us call this as q1. Okay, in this will be, let us say, q2, this will be, let us say, q3, and this side we can have, let us say, q4. As far as vertical component is concerned, so this we can say q5. Okay, this will be, let us say, q6, right? Here vertical, this will be q7, and here let us say we have q8, like this. Okay, so now since there are four nodes, so we need to find first of all the shape functions. Now the best way of identifying shape function is you assume certain displacement polynomial, and you just put the boundary conditions, right? So since these are four nodes, so you need to have at least four constants to define the displacement polynomial, right? So here what I'm going to do is, I'll first of all establish the relationship between, let us say, x with xi as well as y with eta. So this is very much essential. So for this purpose, now I am going to assume the displacement polynomial as x equals to, let us say, a1 plus a2 times xi plus a3 times eta. Okay, plus we have one more term, that is a4 times xi as well as eta. Okay, there are four nodes. So if you remember, in the previous class, when we are going for three noded triangular element, we have chosen only this much of polynomial. Okay, but since there are fourth node, so we have to choose one more polynomial, which will be depending on xi as well as eta, right? On the similar lines, we can also assume the value of y as, let us say, a5 plus This is x6 times xi plus a7 times eta plus a8 times xi as well as eta, right? So on the similar lines, we can have the displacement polynomial, that is u, as well as in terms of v. So u can also be assumed as a1 into q1, sorry, not q1. We can have a1 plus a2 plus we can have this q over here. Okay, this will be a3. So you can have q over here, and a4 we can have q over here. Okay, so on the similar lines we can write this one also. So for the time being, you just forget about this. Let us focus on xi or x in terms of xi and eta. Okay, so all we need to find out what is the value of a1, a2, a3 and a4. So for in order to calculate all this constant, okay, so these constants a1, a2, a3 and a4, what we have to do, we have to apply the boundary condition, that is at node 1. Okay, what are the values of x? So x value will be -1, y value, or rather I should not say x value, I should write xi value. Okay, so xi value will be -1, your eta value will also be -1. Okay, and the rest of the things can be written. So this equation 1, so let us call this as equation 1. So this equation 1 can be written in some form. Then we can have another boundary conditions like this, that is at node 2 we have the value of xi as -1, eta as now sorry, xi will be +1, eta will be -1. Then again we'll have some equation. So on similar lines we can generate four equations. You can substitute the values the way we have done in the previous class, and as a result of this, what you should get is something like this, that is x will be something like n1 x1 plus n2 x2 plus n3 x3 plus n4 and x4. This will be the final output which you will be getting, right? Now here n1, n2, n3, n4, they are nothing but the shape functions. And if you are able to do it, then you will get the n1 value as 1 divided by 4 into 1 minus xi into 1 minus eta. Okay, so this will be the value of n1. Your n2 will be something like 1 upon 4 into 1 plus xi, 1 minus eta. On the similar lines, n3 will be something like 1 divided by 4 into 1 plus xi, 1 plus eta. And your n4 value will be 1 upon 4 into I think this will be minus. Okay, so 1 minus xi and 1 plus eta. So these are the shape functions. So now you can see these shape functions n1, n2, n3, n4, they are depending on the values of xi as well as the values of eta. Okay, so if you want to plot the variation of the shape functions in the three directions, so if you could see, so let us say we have say this will be your, say this is your xi axis. Okay, and this is your eta axis. Okay, and if you substitute, so let us say this is your node. Okay, so I think I have drawn it incorrectly. Let me draw it one more time. So this is like this. Okay, so this will be xi and this will be your eta. And if you could see element, so element will look like this. Okay, so here this will be your node 1, this will be node 2, this will be node 3, and this will be node 4. Okay, so now if you substitute the value of xi and eta at node 1. Okay, so if you could substitute this, so at this point, okay, so I'm talking about this point. So at this point, the value of xi and value of eta, they both are 1, sorry, -1. So here what will happen, this will be 2, this will be also 2, and ultimately what you are going to get n1 value as 1 over here. Okay, so if you substitute the value of n xi and eta at node number 2, so at node number 2 the value of xi is +1. So in that case, this component is going to become 0, and as a result of this, you will get a variation like this. So here this value will be 0. So similarly, the value of this n1 over here, this will be also 0. Over here also, this will be also 0. And over here, it will be like this. So as a result of this, what you are going to get? You are going to get a plane kind of a structure. So this particular shape shows the variation of n1. Okay. So on the similar lines, you can also plot the variation of n2. So this will be xi, this will be eta, and if you could plot the element, so your element will be like this. Okay, and your variation will look something like this. So here the value of n1 will be 1, here it will be approaching to 0, here also it will be approaching to 0, here also it will be 0. So your plane will look like this, right? On the similar line, we can have the variation of n3 also. So this will be xi, this will be eta, and the values will be something like this. Okay, so this will be your element, and the n1 value at node 3, oh sorry, n3 value at node 3, it will be 1, but at other nodes it will be 0. So it will look like this. Okay, and lastly, we can have the n4 variation showing like this. So this will be eta, this will be xi, and if you could plot the element, so your element is like this. Okay, and your variation will look something like this. Okay, I hope this is clear to everybody. ठीक है, किसी कुछ डाउट है? Okay, please note it down. Okay, please note it down. Student, is it okay now? Shall I continue? Yes, student, shall I continue?
Sir, wait for 1 more minute.
Okay, fine. किसी को कुछ डाउट है इन बिटवीन? Shall I continue? Yes, shall I continue? Yes, student, shall I continue or you want some time?
Yes, sir.
टाइम चाहिए कि कंटिन्यू करूं?
कंटिन्यू करो सर.
ठीक, चलो, ओके, ध्यान दो, अभी थोड़ा सा इंपॉर्टेंट है. ओके, सो प्लीज पे अटेंशन, राइट? So now see, this particular figure shows only the variation of the shape function across the element. Okay, and we know that the n1, n2, n3, n4 values, they are now depending on the values of xi as well as values on eta. Okay, So now on the similar lines, you can also get the variation of displacement also. So you can get something like u is equal to n1 u1 plus n2 u2 plus n2 u3 plus n3 u, sorry, I should not write this one, I should write in different way because we are writing it in a natural coordinate system. So this will be something like n1 q1, because q1 is the displacement at node 1 in the horizontal direction, right? Then we can have n2, then q2 plus n3 and q3 plus n4 and q4. Similarly, v can be written as something like n1, this will be q5, okay, this will be n2 q6, this will be n3 q7 plus n4 and q8. Okay, so these are the shape functions, these are the displacement polynomials, right? And ultimately what we are interested in, we are interested in epsilon. Okay, so epsilon is nothing but strain, and it has got three components: epsilon x, epsilon y, and gamma xy. Okay, and if you rewrite this, so this will be something like du by dx, this will be dv by dy, this will be du by dy plus dv by dx. बराबर है? So basically we are interested in couple of terms, that is what is du by dx as well as what is du by dy, because these terms are required over here, okay, here, and this is du by dy is also required over here. Plus we are interested in calculating what is dv by dx, okay, and dv by dy, because these terms are required over here. So here you can see this is dv by dy and dv by dx. Okay, so basically we are interested in the Jacobian matrix, and if you remember in the previous class, we have written a Jacobian matrix. So similar Jacobian matrix will come into picture over here. So here Jacobian matrix is something like this. Okay, so this will be del x by del xi, okay, and this will be del y by del xi, and here this will be del x by del eta, and this will be del y by del eta. Okay, so this can be written in a simplified form, because we already know the x value is depending on the value of xi and eta, and we have just now seen x can be written as n1 x1 n2 x2 n3 x3 and n4 x4. So the same can be written in a derivative form, which is like this. Okay, so here this will be del by del xi of n1, then del by del xi of n2, then del by del xi of n3, and del by del xi of n4. Okay, and similarly over here we can write something like del by del eta of n1, del by del eta of n2, del by del eta of n3, and del by del eta of n4. This can be multiplied by something like x1, this will be y1. Okay, so this will be y1, this will be x2 y2, this will be x3 y3 x4 and y4. Okay, so if you just multiply, sorry, so if you multiply the first row and first column, you are going to get del x by del xi. Okay, so in this particular way you can get the values of this Jacobian matrix. Okay, and if you remember, we have seen in the previous class that the value of this du by dx can be written in a different form, and accordingly what you can get a different values of this Jacobian matrix. Okay, so so if you remember, we have written something like d, ye dekho, let me open the previous one. Okay, so here what we have written is this one. Okay, so du by dxi and du by d eta we have written, and it was dx by dxi, dy by dxi. So everything has to be done, and as a result of this what we have got is this matrix, that is the Jacobian matrix. Okay, so I'm directly writing down the Jacobian matrix. So on the similar lines you can generate this B matrix over here also. So I'm just writing down directly the value of this B matrix over here. Jacobian matrix I have already explained. So your B matrix in this particular case, that is the strain displacement matrix, will come. This will be B. Okay. So this will be something like J, and we have to write down the inverse of that. Okay. So in the previous section also, we have obtained this Jacobian matrix inverse, right? So this will be something like uh, this will be d by d xi of n1 into 0. This will be 0, and this will be d by d eta of n1. Okay, so same lines, this will be d by d eta of n1, this will be d by d xi of n1. So this will be the first component. Okay, here you will be getting d by d xi of n2. This will be 0, this will be 0, this will be d by d eta of n2, this will be d by d eta of n2, this will be d by d xi of n2. So this is the second section. Then similarly we can have d by d xi of n3, 0, this will be 0, d by d xi of n3. So this value will come over here, and this value will come over here. Okay, and lastly d by d xi of n4, 0, 0, this will be d by d eta of n4. I think by mistake I have written xi over here, it should be d eta. Okay, and this value will come over here, and this value will come over here. Now this will be multiplied by, you will have something like q1, this will be q5, this will be q2, this will be q6. Okay, this will be q3, this will be q7, then q4 and q8. Okay, so ultimately you are going to get a matrix which is something like this. Okay, so all we have to do is you just go for derivation of n1, n2, n3, n4 with xi and with eta. Okay, so ultimately you are going to get a B matrix which looks like this. Okay, so we have inverse of this Jacobian matrix multiplied by, so if I if I take out 1 by 4 common, let me write down, this is minus 1 upon 4, this will come something like 1 minus xi, this will be 0, this will be 0, this will be minus 1 upon 4 into 1 minus xi, this value will come over here, and this value will come over here. Okay, so there will be, this is the first section, so this will be something like 1 upon 4, this will be 1 minus xi, oh sorry, 1 minus eta, and this will be 0, and this will be minus 1 upon 4, this is 1 plus xi, this value will come over here, and this value will come over here. Then we have, this is 1 by 4 into 1 plus xi, this will be 0, and this will be 1 by 4, 1 plus xi, this is eta, not xi. Okay, this value will come over here, and this will be over here, and this will be minus 1 upon 4, 1 plus eta, 0, 0, and this will be 1 upon 4, 1 minus xi. Okay, and here the same values will come over here, and here you will have this vector only. Okay, so in this way you have to generate the B matrix, and once this B matrix is generated, okay, so now you please pay attention over here. So once this B matrix is generated, you have to go for elemental stiffness matrix. Elemental stiffness matrix is integration over the volume B transpose into D into B over dV. Okay. Yes, students, please pay attention now. Am I audible correctly? I think I got disconnected. Yes, everybody.
Sir, you are audible.
Yes,
Okay,
sir.
fine. Now please pay attention, and this is an important one, right? So now you see, we have to go for the integration, right? So the problem is over here is this B. B is dependent. Okay, it is dependent on xi as well as eta. Okay, because you see the values of this matrix it contains the terms of xi as well as eta. Both the things are there. Okay, so we have to integrate accordingly. So what we can do is we have to integrate with, let us say, -1 to +1. Okay, again -1 to +1. We can write this is b transpose into d into b. Now dv can be written as thickness into da. Okay, so da can be written as something like this, that is the Jacobian matrix. Then we can have del xi by deta. Okay, so this we have already seen, right? Now here we can use a method called as Newton-Gauss quadrature method, which we have seen in the first year, first sem, in the numerical method subject. Okay, so if you remember, let me go back and just refresh your memories. So if you have a coordinate system which is like this, okay, so we have a coordinate system like this. Remember हम लोगों ने यहाँ पर xi लिया था, याद है? And we have drawn a curve which is like this, and here we have seen -1 and here we have seen +1. याद है क्या बेटा ये सबको? याद है? Integration was what? It is nothing but the area under the curve, right? So if you remember, we have gone for something like w1 f of xi1 plus w2 into f of xi2. Okay, in short, we have written I is nothing but wi into f of xi. तो तुम लोग जितने इंटीग्रेशन पॉइंट्स लोगे उतना तुमको एक्यूरेसी आएगा. एवरीबॉडी रिमेंबर्स दिस? याद है सबको? यस, एनीबॉडी? याद आया कि नहीं आया? अरे कोई तो बोलो.
Yes, sir.
ठीक, याद है ना? पक्का?
Yes, sir.
Yes, sir.
Okay, so we have to go for the integration at each and every point. Okay, so here you remember we are taking this xi value, where this xi value was given to you. याद है? So this xi value, so if I take two integration points, okay, two integration points. Okay, so if you take this two integration point and if you want to have the accurate result, so here we have taken these two integration points. Okay, and it was something like 1 upon √3, if I remember correctly, isn't it? And its weightage was given as 1. Okay, so here on the similar lines we have to go for now integration, but this is a 2D case, because you see over here this is a double integration. You have to integrate for xi as well as you have to integrate for eta. So here, in place of going for two integration, because this was in 1D, so now if this is your element, if this is your element, it's a square element having size 2 by 2, and here we are having your origin. Okay, आपका origin कहाँ पर है? This is your origin, right? So here you have to integrate at 4 different points, because this is a two-dimensional figure. So one point will be over here, one point will be over here, one point will be over here, and one point will be over here. So here your expression, that is this integration. Okay, so this integration will be something like wi f of I. Okay, but this I value will be from first point, second point, third point, and fourth point. Okay, so where we have to integrate for 4 different points and we have to add them, then and then only you will be able to get the integration. Okay, so now basically when you are solving a problem, what we have to do is we have to generate this B matrix. Okay, so if you remember ये जो B matrix है, so this B matrix is having a terms of xi as well as eta. तो ये जो xi और eta की वैल्यू है पहले तुमको ये पॉइंट की लेनी पड़ेगी. Okay, and then you have to go for the multiplication of this entire B transpose into D into B, and all this thing you have to do. Okay, so that you can get the first part, that is w1 into f of xi1. Okay, where w1 value will be only 1. Then you have to go for another integration point, so you will get w2 into f of xi2. Then you take one more integration point, you get w3 f of xi3. Then you take one more integration point, so this will be w4 and f value. Okay, So you have to generate four different stiffness matrix at four different points, and then you have to integrate this. Okay, so it's a very time consuming task. So in the examination part you won't be asked to generate a stiffness matrix, but you should know how the stiffness matrix is generated, and the detailed explanation of this and the detailed solved problem is given in the N Krishna Raju book, based on the finite element method. Okay, so let me stop over here. I am not stopping the recording because I have to show you the numerical part. Okay, just give me a moment, please remain in the class, just give me a moment. Okay. Let me open the Excel sheet. Yes. Uh, Let me start sharing the screen. Okay. Is my screen visible to everybody? Yes, student. Is it visible?
Yes, sir.
Okay.
Yes.
Your recording is still on, so that's good. So please pay attention. Okay. So here,
सर
what?
जूम करिए थोड़ा.
Sorry.
Zoom zoom.
Zoom करना है? Okay. ठीक है. Fine. No issue. Okay. So what I have done, so let me explain the problem first. Okay. So basically it's a plane stress problem. Okay, the value of E is given to you, value of mu is given to you as, let us say, 0, and the thickness of the plate is given to you as 20 millimeters. Okay, so since this is a plane stress case, so we already know the value of the D matrix. Okay, D matrix is nothing but your stress strain matrix. So if you remember, there is a constant which is coming outside, that is E divided by 1 minus mu square, and here over here this is 1, this is also 1, this is also this is 1 minus mu by 2, this is mu, this is 0, this is also 0, this is also 0, this is mu, this is 0, and this is mu. Okay, so we have already seen this. So based on this we have calculated the value of B matrix, sorry, value of D matrix. Okay, now here I am taking a simple problem. So in this problem, the this is a element number 1. So there is only one element, it has got four node 1, node 2, node 3, and node 4. So if you see, node 1 is having coordinate 0 0, node 2 is having x as 40, y as 0, the third node is having x as 40 and y as 30. So basically it's a rectangular plate which is having the width or the length of that particular plate as 40 millimeters and the height of the plate as 30 millimeters, right? So now if you remember the integration points, so like I told you, the weightage for the integration point is so if you take 2-point integration, so 2-point integration in xi direction, 2-point integration in eta direction, so the integration point has to be taken at a distance of 0.5577. Okay, so the corresponding weightage will be 1. Okay, so this is the integration point. So if you take this integration point, so you have to first of all calculate the J matrix. Okay, I think let me share my entire screen so that you can get a clear picture along with what I have taught today. Okay, fine. So it is coming up, right? So I hope my screen is visible to everybody now. So
Yes, sir.
what I was telling you is this. So here I have taken only one point. Okay, so one point is x is, sorry, the xi is 0.55577, eta is 0.577. So here I am talking about this point. Okay, so this is your point number 1. Okay, so let me note down over here. So this is my point number 1, right? So here so the xi value as well as the eta value both are positive, right? So since both are positive, so I have to generate this J matrix first of all. And if you see this, I have already shown you the J matrix. So J matrix is nothing but d by d xi of n1 n2 n3 n4 and d by d it of n1 n2 n3 n4 multiplied by x1 y1 x2 y2 x3 y3 x4 y4. So the same thing I have written over here. So this is d by d xi of n1 n2 n3 n4 d by d it of n1 n2 n3 n4 multiplied by this is x1 y1 x2 y2 x3 y3 x4 y4. So if you multiply this row with this column, what you are going to get? You are going to get this as 20. Then you just multiply all this thing, you are going to get this matrix. So this matrix is nothing but your Jacobian matrix. So if you take out the determinant of this Jacobian matrix, so this will be simply 20 into 15 multiplied by this into this, oh sorry, minus this into this. So ultimately you are going to get the determinant of this Jacobian matrix as 300. Okay. So once you get this determinant of the Jacobian matrix, you have to find out the inverse of this Jacobian matrix. So inverse of the Jacobian matrix will be something like 1 upon determinant of J multiplied by, so this 15 will come over here, this 20 will come over here, and this will be having the negative sign. So inverse of Jacobian matrix will look something like this. Okay. Then your B matrix. So if you see here, I have written B matrix. So B matrix is first of all the inverse of this Jacobian matrix multiplied by, you can have something like this one. Yeah. So this is your Jacobian matrix. You can this is your B matrix. So B matrix over here, this is inverse of the Jacobian matrix minus 1 by 4 into 1 minus xi, and this entire matrix will be there. So you just substitute these values. So you are going to get this B matrix. Now remember, this B matrix calculation is done for point number 1. Okay. And this is your point number 1. That is xi value is so and so and eta value is so and so. Okay. So this B matrix is ready with me. Then I am just going to multiply D with B. Okay. So this is D with B. And then I am going to multiply B transpose into D into B. So this big matrix will come into picture. And then apart from that, we have a constant which is coming out. So if you see this in the over here, so the thickness will come out, this Jacobian matrix will also come out. So all these constants will come out, and as a result of this, what you are going to get is this. This is nothing but the stiffness matrix, but this stiffness matrix is generated for this point. That is point number 1, that is 0.557 in xi direction and 0.577 in the eta direction. So I am talking about which point? Point number 1. तो यहां तक समझ में आया सबको? किसी को कुछ डाउट है? Yes students, is there any query? समझ में आया सबको? ठीक है. So now we have to repeat the same thing. Now we just have to change the point, because I have to go for numerical integration. So in the second point, I am going to take this second point. Okay. So this is my second point where the xi value is negative and eta value is positive. So basically I am talking about this point. This will be my second point. So here the xi value is negative, so I am going in the negative xi direction, but your eta value is positive. So everything will remain same. Okay, your B matrix, your D matrix will remain same. Only thing is, now since your xi and eta terms are changed, your Jacobian matrix itself will change, because you see the Jacobian matrix, if you see the Jacobian matrix, it is like this. Jacobian matrix is d by d xi of n1 n2 n3 n4 and so and so. But the xi values are now changed, because n1 is a function of xi as well as eta. तो यहाँ पर देखो हम लोगों ने लिखा है, so n1 is depending on the value of xi as well as on the value of eta. So since xi and eta is changed, so this particular matrix is going to get changed. Your x1 x2 x1 x2 x3 x4 y1 y2 y3 y4, they are going to remain same. So as a result of this, what you will find, this matrix is completely changed, but your determinant of J is exactly same. So accordingly, you have to find out the inverse of the Jacobian matrix, get the B matrix, because B matrix is already, I have shown you, this is your B matrix. So all you have to do is just calculate this B matrix, multiply with D, multiply B transpose with D, and if you get the constant, so as a result of this, you are going to get this entire K matrix. Okay. Now again, this K is for a point. So this is your second point. Okay. Now let us talk about K3. So this is your third point. So this is the third point. So this third point is both are negative. So here I'm talking about the third point, which is located over here. So for this point, again, you have to go for this. So the xi value will be negative, the eta value will be negative, the weightages will be 1 and 1. So since xi and eta is changed, this J matrix will also change. Accordingly, the entire calculations are going to get changed. And as a result of this, you will be getting this K3. Okay. Now K4. Now in K4, you have to change the xi and eta value again. So this K4, the xi value is positive, then eta value is negative. So this is nothing but your fourth point of integration. Okay. So this fourth point of integration, again, since the xi and eta values are changed, this will change, and accordingly everything is going to get changed. So now you have 4K. That is, what is the stiffness matrix with this point of integration, with this point of integration, this point of integration, and this point of integration. So basically you have Wi into f of xi I, where xi value is 1, 2, 3, and 4. So this is K1, K2, K3, K4. All we have to do is assemble this, or I should say add this. Okay, because here you see this is if you see the expression of I. So let me write down over here. So I was something like W1 f of xi1 barabar hai W2 f of xi2, and so on. It was a summation. Okay, here I have already written over here. So all we have to do is just add K1, K2, K3, K4, and as a result of this, you will be getting this much of big matrix. Okay, so this is nothing but a stiffness matrix for one element. Okay, again I am saying this is the stiffness matrix for one element. Now remember, if you want to do the calculation for a problem which is having, let us say, two elements, so in that case you have to calculate the stiffness matrix for the second element also using the same process. Okay, so it's a very time consuming task, but you should know how to do it. Okay, so now here you see I have already generated this stiffness matrix. I have written some force matrix over here. I have calculated the unknown displacement, and then I can easily calculate the stresses and strain at different points. Okay, so this can be easily calculated because the value of strains are known to us. Okay, this is nothing but your B matrix. Okay, so B matrix is known, and B, we know the B matrix at point 1, at point 2, at point 3, and at point 4. Okay, so let me explain you one more time. So what we have done over here, we have calculated the stiffness matrix. Okay, for this point, for this point, for this point, and for this point. Okay, so for calculation of the stiffness matrix at point 1, we have first of all calculated B1, that is the strain displacement matrix. So strain equals to B into displacement. So if you calculate this K1 plus K2 plus K3 plus K4, so you will be getting a big K, and this big K will be multiplied with this force, and what you are going to get, this is unknown displacement. Okay, so once this unknown displacements are known, so let us say I want to calculate what is the stresses at, let us say, center. Okay, so I want to find out what are the stresses at the center. What should I do? I should first of all calculate its B. Okay, or B कैसे calculate करोगे? By substituting the value of xi and value of eta as 0. Why I am saying 0? Because in the basic assumption here, at the center point, the value of xi and eta both are 0. So you have to first of all calculate what is the value of B for the 0 point. So once this value of B is known, okay, so value of B is known, all we have to do is just multiply with delta. So you are going to get the strains, and the strain is having three component: epsilon x, epsilon y, and gamma xy. So for this, for getting the strains at this point, you should know what is the B value. Okay, for example, I want to know what is the strain at, let us say, this point. Okay, so at this point the value of xi is -1 and value of eta is 0. So again, if you want to know the strains at this point, so what we have to do is first of all get the B matrix. Okay, then multiply with delta so that you can get the strain. Okay, so similarly if you want to know what is the strain at this point, so at this point the value of xi is 0 and the value of eta is 1. So in this way you can get now the variation of stresses within the element. Okay, so this was not possible in CST because within the element the strain and stresses they are considered as constant, but with the help of this rectangular element now you can get the variation of stresses within the element. Okay, so this is much more advanced, but definitely it is going to cost you a hell lot of calculations. So for this purpose manual calculations are not at all recommended. Either you write your own program or you use the excel sheet the way I have shown you. Okay, so this is the only method by which you can reduce your calculations, but definitely this is going to give you a hell lot of greater accurate results. Okay, I hope you have understood this. ठीक है बच्चों, is it okay?
Yes, sir.
Yes, sir.
ठीक है. So I tried my level best to explain you the things in proper way. I am sure तुमको समझ में आया होगा. In examination point of view, most of the most common question asked is like this. Let me share the screen one more time. Okay, uh, so in exam what is asked, let me explain you. Okay, so in the exams, so one figure will be given to you. Okay, so this will be a figure. Okay, and some element is given to you. Okay, so this will be some kind of a element, right? So now this will be having some coordinates, let us say x1 y1. So these are values will be known to you. So this will be x2 y2, this will be x3 y3, and this will be x4 and y4. Okay, तुमको क्या पूछेंगे कि ये पॉइंट है P, ठीक है, इसका x और y तुमको दिया है, ठीक है, तो तुमको क्या करना है, इस पॉइंट पे जैकोबियन मैट्रिक्स निकालना है. ठीक है, तो if you want to calculate the Jacobian matrix at that particular point, what you have to do, we already know the Jacobian matrix at that particular point is like this. आ गया? Okay, so it is nothing but the d by d xi of n1 n2 n3 n4 multiplied by x1 x2 x3 x4 and so on. So okay, we already know values of n1 n2 n3 n4, they are already written over here, but here the value of n1 is depending on xi and eta. Okay, और हमको क्या चाहिए, ये point. So we know the value or the nodal coordinates of P in terms of x and in terms of y. We don't know what is the value of xi and we don't know what is the value of eta at point P. तो पहले तुमको क्या कर निकालना पड़ेगा, तुमको xi निकालना पड़ेगा और तुमको eta निकालना पड़ेगा at that point. And how you are going to get the value of xi and eta for that point P? Using this one, that is this one, x equals to n1 x1 n2 x2 n3 x3 n4 x4. So here n1 n2 n3 n4 values are there in terms of xi and eta, and similarly the y is also written in the same form. So y will be n1 y1 n2 y2 n3 y3 and n4 y4. So this will be known to you. So if you expand this particular expression, so for example over here, so you have say x equals to say n1 x1 plus n2 x2 plus n3 x3 plus n4 and x4. So here this value will be known to you. Okay, ये तुमको पता है. Okay, x1 is known, x2 is known, x3 is known, x4 is known. Okay, because these values are already provided over here. Okay, we don't know what is the value of n1. So n1 value is depending on either xi or eta or both. n2 is also either xi or eta or both. This is either xi or eta or both. Same with this one. Okay, so basically you have one expression with two unknowns. Okay, so you can generate similar kind of expression for y also. So y is nothing but n1 y1 plus n2 y2 plus n3 y3 plus n4 and y4. So here also n1 is depending on this. Okay, this is also depending on this. Okay, and value of y will be known, this will be known, this will be known, this will be known, this will be known. So you have another equation which is having two unknowns. Okay, so now you have two unknowns. Okay, and we have two equations. So definitely we can solve this. So once you solve this, what you are going to get? You are going to get the value of xi and eta at this point, that is at point P. And once the value of xi and eta are known to you, you can get the Jacobian matrix, because the Jacobian matrix is like this, that is n1, n2, n3, n4. So you can definitely go for value of n1, n2, n3, n4, and ये वाला तो तुमको already पता ही है. So this kind of question, which is relatively simple, is asked in the examination. So I am going to put a simple question in the upcoming assignments, similar to this one, so that it will give you a practice. Okay, I hope this is clear to everybody. ठीक है? Yes, student, is it okay? Yes.
Yes, sir.
ठीक है then. So I am stopping over here. Tomorrow's class will be conducted by Gharat sir. He has organized one guest lecture for you. So I won't be taking tomorrow's class, but I'll be needing one more class. So probably day after tomorrow, I think we have holiday. So if possible, I'll conduct the FEM practical on holiday itself, so that we can complete the last practical. So the only last practical is remaining, and one introduction to three-dimensional finite element analysis is pending. So probably someday I'll engage one extra lecture, and I'll cover that one also, so that your entire syllabus will be over. Okay. So this is all from my side. So if you have any queries, you can remain in the meet.